Hello, welcome to Open Logic. In this video, we're going to look at a writing test bench with classes. Previously, we have looked at the simple directed test. It has a top-level module, and inside the module, it has a design. Also, inside the top-level module, we write execution code to derive and monitor the design. You can refer to this video to refresh on the simple directed test. Now, before we proceed, is it good or bad to write tests in this manner? It actually depends on the intent. If you have a small design or if you want to have a quick experiment, this is a quick and easy way to achieve that. But if you have a large design or if you wish to develop reusable test components, then this may not serve the purpose. Today we will try to develop a test bench which is good for large design, and we will develop reusable test components. First, let's try to visualize the test bench in a graphical manner. We will still have a top-level module and a design. If it's possible, the design should have functional ports instead of individual input or output wires. And we would have an equivalent test bench with a matching functional ports. Between the design and the test bench are interfaces which are used to connect the two. The test bench is a placeholder where tests are written. To run a test, we need to instantiate the test and run it. Generally speaking, this is a simple test bench structure. If it's possible, we will try to write components according to this diagram. However, this diagram is generally incomplete, and there are many second-level details which will make the final component's code deviate from the diagram. For example, who is responsible for generating a clock? The clock can be driven by the test bench, or it can be driven by an external clock source. These kind of decisions, some of them are trivial, but some of them will change how the final test bench looks like. Alright, first let's start with the interface. I have split the interface into two. One is for data and another one is for config register CR. This is the data interface. It has an input clock. These are the signals it contains. There are two mod parts. One is meant for the design and another one is meant for the test. Similarly, this is the config register interface. It also has an input clock, and these are the signals it contains, and there are two mod ports as well. Now, before we continue, we can also write the interface in this manner, where both the data and config register signals are in the same interface. And can you tell which one is better? Well, these two interfaces are segregated components with dedicated functionality. They are therefore easier to be reused, whereas this one is one big interface with mixed functionalities, which limits its reusability. Imagine if you have another design with a different functionality, but it has the same config register signals. The new design can then reuse this interface as compared to this one. However, having two interfaces means it's harder to integrate and synchronize them, whereas this one doesn't have the same problem. We'll be using these two interfaces in this series. Note that for both the design and the test, clock is an input, and that means there is an external clock generator. We'll be using another interface to model the clock generator. It has a clock wire and a time period, and it generates clocks upon the instantiation. Now, according to the diagram, this should be a module. Can you tell the difference between using a module and an interface in this case? If we are talking about generating clock, module and interface are the same. However, interface can be passed to classes as a virtual interface, and therefore it is more versatile. Now that we have these three interfaces, we need to instantiate them in the top level. Note that the data interface and the config register interface, they both take in the clock from clock generator. And now the design. This is the design in a short-formed manner, and this is to instantiate the design in the top level. We connect the interface wires to the design wire ports one by one. Now again, if we are to follow the diagram, this is not exactly what we want. we need to change the design so that it uses the interface mod port instead of individual wires. Then we can instantiate the design in this manner. Generally speaking, this would help integration. Imagine in the future the interface add or remove signals. This instantiation will not be impacted. However, in my years of experience, I have never seen a single design using interface mod port. I can guess the reasons, but that would be speculative. However, one thing for certain in this case, if we are using these two interface mod ports that each has an input clock, it means that there are two input clocks to the design, which is different from the original one. I believe it is things like this which makes the designer stick to the older way, and for this series we will follow that. For the test bench, we will be using program, and we can use the interface mod ports as functional ports. In the top level, we can instantiate the test bench program like this. And now the test in classes. Let's assume we have only one test for now. We can write the test inside the program, then we create a handle for it, and then we instantiate it. Well, it is only reasonable the test requires the data interface and the config register interface, so we pass them in through the constructor. The test should have a task where it carries out execution. Let's call the task run, and we can call it here in the initial block. Now inside the test, it has two virtual interfaces, one for the data and one for the config register. It also has a constructor. This constructor requires user to pass in the interfaces when instantiating this class. It also has a virtual task called run. This is where the test drives and monitors the design. And there you go, we have a simple test bench with classes. Now let's get back to the beginning. Why do we bother to write a test bench in this manner? Is it worthwhile? Well, there are three reasons. First, clarity. Second, maintainability. And finally, reusability. Every module, interface, and class has a specific functionality. It helps you to understand how they work, as compared to one big piece of code. For example, this top-level module, it is a placeholder for integration. It tells you what components it has, and it gives you an idea of what each component does. The interfaces are used for connectivity. Having said that, they also serve other purposes. If you need to introduce output delay to certain signals, you can use clocking block. It is therefore easier to maintain. Adding output delay in a directed test across many lines of code, it would be tough. The clock generator is highly reusable. Wherever you need a clock in any design, you can just instantiate it. The test program is a placeholder for test classes. We'll discuss more about it in future videos. The main focus for the rest of the series will be on writing the test classes, and the UVM is mostly about that. Mostly. But let's not jump into the cockpit and fly right away. Let's go step by step. Looking at this class, how can we make it clearer, easier to maintain, and reusable? Well, for starter, all this execution code here, we can use tasks to wrap around them. For example, reset design, send input, monitor output, and so on. That gives a better idea on how the test works. This is the reset design task. It drives reset to 0 and after a while back to 1. This is the send input task. It sends random data for one clock and drives data and data value to 0 after that. I'll skip the monitor output task for now. We'll write a proper one in future video. But you should get the idea. That is to create the task based on intent. Besides being clear, the tasks are also reusable. Let's say we have a new test, test 1. In the worst case, this class can be totally different from test 0. Instead of having a task called run, maybe it has a task called start or execute or main. But it's best to standardize the task name so that everybody knows where to look in the test. In fact, one way to standardize a task is by using class extension. Let's say if test1 extends test0. It doesn't need to write the two virtual interfaces because it inherits them from test0. However, it needs to have a constructor because unfortunately constructor cannot be inherited. I will make another video to talk about the constructor. Now, practically, you can call test1.run. It would be the same as running test0. But say we want to make some modification. We want to send a specific data instead of sending a random one. We can override the send input task. If we call run now, it will call reset design and then call this overridden send input and then monitor output. Or say if we want to reset while a conversion is ongoing, we can override the run task like this, where we reset the design and then send input, and 2 clocks later we reset the design again. Note that in both cases we only override one particular task. All other tasks are being reused from test 0. Of course, this is still a very crude way of using class extension. This is just a demonstration to make a class clear, easy to maintain, and reusable. In future videos, we'll look into writing proper classes for reusability. Alright, that's it for this time around. Thanks for watching. And oh, before you go, do help to support by clicking like, share, and subscribe.